what's our goal? If we're trying to find the vertical asymptotes of this function. First of all, where's that happen again? Where do we find vertical asymptotes? Say it again. Okay, at the zeros of the, okay, but if I'm looking at this rational function, I asked a bad question. Let me be more specific. Okay, so this function right here is this rational function is gonna have vertical asymptotes when what happens to that function? Denominator is 0 and the numerator is not 0. Okay, so our goal then is just to find the zeros of the common, or the unique zeros of the denominator. And so to do that, we said we can use graphing technology. It's a graphing calculator test. And yesterday or day before, I guess, we graphed this function and looked for the x-intercepts. And did we finish?
Yeah, we finished.
We finished doing that one. There's some other ways to do this as well. Now let's see. We said we could graph it. We could use the quadratic formula. I'm going to show you kind of a, well, let's see, on this calculator, let me check one thing here. Do I have it? I'm not sure if you have this or not, but I'm going to show you one little trick here too. I almost hate to even show this to you because it's so good, and it allows you to really skip through things. Yeah, there it is. It's a horrible name, polysmol 2. It's polynomial simultaneous equation solver version 2, I guess. So check and see if you have this on your calculator. This is a good one. If you don't have it, I can download it for you. Nobody has it? You have it? Raise your hand if you do have it. It's in apps, in the apps folder.
I got it.
Got it? Got it? Okay, let me show you how to use this thing. This is really an effective way to find zeros of some kinds of functions, of polynomials in particular. So if you go down to this thing and turn it on, what's it say? Press any key, continue. You get a choice. You can do a bunch of stuff up here. The one we want is number 1, polynomial root finder. So if we hit enter, look what it does. It gives you this control panel, and you can choose the order of the polynomial. Now, what's that mean? Highest power of x. Okay. So in our case, it'd be 2, right? You get your choice. Do you want to find, look, this is kind of cool. Do you want to find real, or do you want to find complex solutions with imaginary parts? And there's 2 different ways. You can have them written in the rectilinear form, which is a plus bi, or you can even have them written in polar form, which we won't really get to this year, but in college that'll be handy. You can have numbers written as decimals or even as fractions, which is pretty cool. And you can choose the degree, like if you're doing decimals, you can even choose how many sig figs you want. But for us, this is kind of the default setting. We're looking for real solutions, right? And I guess we'll choose fractions. Why not? Actually, it wants decimals, doesn't it? Although we can just take the answer and convert it to a decimal. Okay, so this is all set up then. Once you get this thing set up the way you want it, you go next, which is these soft buttons at the bottom. That would be F5. And you get to just choose the coefficients. Isn't this cool? So notice it has to be in standard form, of course, right? But then if we're trying to find the zeros of the bottom, a sub 2, which is the coefficient of x squared, would be 1. Okay. Go down. A sub 1 is negative 3. And a sub 0, negative 24. Okay, and then if we just hit solve, F5, look what it does. Isn't that good? That's a pretty good deal. Yeah. And I guess I don't feel bad having you, I mean, because if you're gonna use graphing technology on the graphing technology portions of the tests, I want you to go for it. I mean, just get to know these things really well and use them as tools, because they do amazing things very quickly and efficiently. So that would be a quick way to do this too. And then all we'd have to do is do the same thing for the numerator and just compare the zeros and see if these zeros are in fact unique, right? And we found out that they were, right? Make sense? Okay? That's a good one. All right. So what else do we have trouble with here? Let's get back on track here. Okay, what about this one? There were some questions. I kind of pulled up some questions for it was it'll be number 4 on the test that this caused some problems. Define g of 4 for the given function so that it is continuous at x equals 4. And we'll take a look at a couple other versions of this. We won't necessarily do them all, but just talk about how they all mean the same thing. So we've got this function that is, as it's written, g of x is discontinuous at x equals 4. What happens if I plug in x equals 4 here? I get 0 over 0, right? Okay, so that's a hole in the function, right? So the ant's walking along, and there's a pothole at x equals 4 where he just blinks out of existence and he steps there, just that one point. We need to define the function so that we fill in the pothole, right? So that when he steps on x equals 4, he's standing on terra firma instead of the hole in the function, right? And so what that really might end up looking like is something like this. We've got this piecewise function. We could define this as a piecewise function where one piece of the function is the rational function as presented. So it's 8x squared minus 128 over 8x minus 32. And that's going to be the function on the domain everywhere except 4, right? That's the function that's defined every place except x equals 4, but it's undefined at x equals 4 because we've got that 0 on the bottom and the top, turns out. So we need to know then, what are we going to put there when x equals 4 so that it's continuous? In other words, we're going to add a point at x equals 4, but we got to put it in the right spot. What we don't want to do is this. We've got our function. And who knows, I'm not going to, who knows exactly what it looks like. Probably something like this. Right? Something like that. There's g of x. Where are we going to add that one point? Now, we don't want to add it up here or down there. We obviously want to put it right there, right? So it fills in the hole. How are we going to know the y value that we need to choose then? Second calc value. Okay. Okay. I see what you're saying. We've got our graphing calculators available, so let's lean on them here a little bit, see what we can do. Now, the problem with that, I just need to get out of this, don't I? Main, quit. So, okay, if I go up to y equals and I graph this, so I've got the quantity 8x squared minus 128 divided by quantity 8x minus 32. There we go. Okay, so if I graph this, just say maybe zoom standard, see what happens with zoom standard. Okay, the problem is going to be what? If I go value, calculator's not going to tell me anything because it's not defined there, right? Now maybe I could choose, I guess, how could I maybe use the graph to do this though? Okay, I could pick a value really close. Like what if I picked 3.99999, something like that, right? But what am I really getting at there? I'm graphically trying to evaluate what? Okay, there's a hole there, but if I want to find, Well, what's the math term for what I'm trying to find? If I wanna know where to fill in that pothole,
Continuity.
okay, I'm trying to make it continuous, you're right, but how do I know the place? Now, slow down for just a second here. If I wanna know where's the place that ant needs to step to fill in the pothole, what's the mathematical question that answers, the limit, where's he think he's gonna step? I'm really just taking the limit, aren't I? We can evaluate a limit graphically, we can evaluate a limit numerically, or we can evaluate a limit analytically. But this would just be the graphical kind of shortcut, right? If I want to know, if I plug in a value, if I take a shortcut and go trace 4, the calculator doesn't give me back a value because there's a hole. But if I want to get right next to that, I could say, how about trace 3.999, and it's going to give me back a y value of 7.999. What's it probably trying to tell me? 8. So, 8's a pretty good bet for our answer. That's a little bit inexact, isn't it? I mean, because we're putting in a finite value instead of looking at an analytical exact answer. But, on a test, if you're trying to do something quickly, that's maybe a way to do it. How else could we do this one? Other than graphically, to tail. Yeah, this is one where we could factor, isn't it? We could, although this isn't, that's a good idea. I think it's a real good idea. So the answer is probably going to be 8, right? We want to fill in the pothole at 8. But we could also maybe do this analytically, pretty quickly too. So talk to me about what I could do analytically here. Factor this thing. Oh, good. Factor out a greatest common factor. Factor an 8 out of the top. And I'm going to get, what, x squared minus 16? On the bottom, factor an 8 out, and I get x minus 4. 8's cancel. Yeah, and then the numerator factors into just the difference of squares, right? There you go. Okay, good. So we get cancellation, cancel like factors. Now I can take my limit. I can evaluate directly. If I let x go to 4, I get 8 for my answer, right? Okay, make sense? Okay, so that's one of the many forms that question could have taken. I just want you to see, these are real common types of questions that you can see on calculus tests at all levels, and you want to be familiar with this. So give a formula for the extended function. Now that's a new term, doesn't show up in our textbook, but you'll hear it in calculus quite a bit. An extended function just meaning the function that fills in the hole. How could I extend that function by adding a single point and removing that removable discontinuity? That's what that refers to. So, same kind of a deal. We've got a hole at x equals -6. We want to take a limit to find out what the y value would need to be for me to fill in that pothole, right? And then one of these answers turns out D, I guess, is the right one. But that's the same question. Okay. If I take the limit, -12 is the y value that this function wants to have, that the ant anticipates stepping on when x approaches -6. Okay? As x approaches -6 from the left, if I try to evaluate this directly, what do I get? Okay, I'm getting a number on the top, right? Yeah, and then what on the bottom? Yeah, okay, good. I'm going to get a 0, right? So previously we would have said no limit, but we want to be more precise than that. No limit means it's a vertical asymptote situation, so the function explodes vertically. We want to know it's going up or down towards infinity, right? As we approach -6 from the left, is the ant climbing an infinite hill or is he dropping into an infinite valley, right? So let's evaluate the limit. On the top I get, if x approaches -6, from the left or the right, doesn't really matter here, -6 times -6 is 36. I'm getting a positive constant in the numerator. What about the denominator? What is this going to become? X plus 6 as x approaches -6 from the left. It's going to 0, but is it going to be a small positive or a small negative result? Small negative. I'm taking numbers like -6 point something, right? And adding that to +6. So there's going to be a little bit of negative overlap, a little bit of negative leftover. So we call that a 0 minus, right? Now remember, if we got a 0 on the bottom, we know it's infinite, but in this case, what's the sign of the infinity going to be? Negative. Yeah. All right. How do I say an odd integer? How do I say an even integer? If n could be any integer, 1, 2, 3, 4, -1, -2, how do I say an even integer? What do I do that? And, okay, yeah, okay, but if I say, it's good suggestion. If I say n pi over 2, look at the problem we have. See, that's suggesting that n could be, like we could have n be 0 or 2, and those wouldn't work. I have to have, somehow I have to trade that n for just the set of odd integers. How can I find the set of even integers? If n is 0, 1, 2, 3, 4, 5, 6, 7. How can I ensure that I'm getting back even results? N pi minus pi over, okay, so if I do that, n pi minus pi over 2. That works great if n is 0, right? It works great if, actually that would work, wouldn't it? That's one way of doing it. Yeah, because if I'm always subtracting, this is going to give me these spots, and I'm just going to back off by pi over 2. That's one way I could do it, sure. There's kind of another more traditional way we do it, and see if you can go back to my original question. If n represents, let me write it down so you can look at it, that might help. Here's n. How can I ensure that I'm getting back even results? What do all even numbers have in common? 2, 4, 6, 8. Divisible by 2. Aha. So what could I do to the set of integers then to make sure that they're even? Not divide by 2. Multiply by 2. Yeah. Look what happens if I multiply all those by 2. I'm going to get now -6, -4, -2, 0, 2, 4, 6, right? So then if n represents a set of all integers, 2n is always even, right? So what's always going to be odd then? Say it again. I think I heard it. Well, how can I take that set and just stagger it a little bit? So instead of picking all the even ones, now I want to get the odd ones instead. If we know that 2n is always even, then what's always odd? 2n plus 1, or 2n minus 1, right? Does that make sense? Because if this is going to get me to all the even hash marks on the real line, then if I just either advance myself forward by 1 or back by 1, all those even, those even increments are going to get shifted to odd, right? So that's our math trick for identifying all of the odd integers. 2n plus 1 or 2n minus 1 is always odd, right? And so then if we want to identify the angles, we can now do that. So theta has to equal 2n plus 1 times pi over 2. right? Which is really what Marie suggested. That's if I just split this into separate fractions, that's what we were doing, isn't it? Because 2n over 2 is just increasing, right? Okay. So there's my angles, but now theta is not equal to x. Turns out theta is equal to 2x, right? I'm taking the cosine not of theta, I'm taking the cosine of 2x, and so what's the last thing I have to do to solve for x? Divide by 2, yeah. If I just divide both sides by 2 or multiply both sides by 1/2, same thing, that's just going to make that a 4 on the bottom. Make sense? So my answer then, if I want to find out all the vertical asymptotes, it's going to be at 2n plus 1 pi over 4. Okay? Make sense? Yeah. Questions on that? All right. Okay, those were the, and if you have any more questions on the test, we'll be in the lab tomorrow. You feel free, come on up and we pull up your test and we go through some individually. Those were the main, as a class, those were the problems we had the most trouble with. Okay, what I want to look at today, I want to move on to something really cool. Let's take a look at what's known as the tangent line problem. This is where differential calculus came from. This is a really cool approach to solving what seemed to be an intractable problem. No one had come up with a solution to this. It seems like a really simple thing. If we want to, we've got some function f, and the goal of differential calculus was to find the slope of a tangent to that curve. Okay? Now we're able to do slopes of secant lines with non-calculus. So for example, if I've got a point here, let's call this point C. I'm gonna make sure I do this same way the book does. And there's a bunch of different ways that people can express this. I think we use x plus c in this book, but let me just verify that. Okay, so we're going to call this C, and then we're going to call this point out here C plus delta x. So in other words, the distance between those points is delta x. Okay. Now if I want to find the slope of the tangent to the curve, all I've got to do is just use what we call the difference quotient. It's rise over run, right? So a tangent line is just a line passing through each of these 2 points. Draw that. So okay, good enough. So there's my tangent line. Right, if I draw a slope triangle, well, that's delta x, right? I could call this, if I want to, delta y. And the slope of the secant line is just rise over run, right? It's just going to be delta y over delta x. Okay, now then let's be a little more precise with what that delta y and delta x mean.
Right.
What are the coordinates of this point right here? Oops. What are the coordinates? Actually, let's do this one first. What are the coordinates of this point? Good. C, I'm hearing, right? Is the x coordinate. What's the y coordinate? If this function is f. F of c, sure. Okay. What are the coordinates of this point going to be? Okay, c plus delta x. And f of the quantity c plus delta x. Okay, so then what is the change in y? What's delta y equal to? If I look at these y values, you told me this one is f of c, and this one is f of c plus delta x. So what's the change in y? Good. So f of c plus delta x minus f of c, right? And delta x is, well, just we defined it as delta x, right? And so then the slope of the secant line, we'll go down here, we could write a little more precisely as f of c plus delta x minus f of c over delta x, right? Okay. And what that's giving us, by the way, is what's called an average rate of change. I like to couch things in physics terms, being as my background is in physics, so I want to give you a concrete physics example. Instead of using, let's say, just a random f of x curve, let's make this a kinematic. How many people are in physics? Oh, good. Good. Let's look at this in terms of kinematic quantities. And if you're not in physics, it's okay. It'll still like this. Let's look at this in terms of position versus time. Instead of x and y, we're going to call this position x as a function of time, right? And so can anybody tell me what kinematic story am I telling with this curve? If this is the position versus time graph, what am I doing there? So let's say that we're looking at position from, here's the starting line, that's the positive x direction. What kind of story am I telling here? Okay, I'm accelerating, aren't I? I'm starting off with my change in position being relatively small, and I'm picking up speed, aren't I? I'm accelerating. So I'm starting slow, and I'm just picking up speed, right? Okay, if I want to know, let's take a look at the slope of the secant line from, let's call this, these are in seconds, so let's say from 2 up to 4, something like that. Okay, so from there to there. Right. If I find the slope of the secant line, here's my line. Okay, what does that represent? Okay, say it again.
Average acceleration.
Not average acceleration. Look, think of the units of this now. If I'm measuring, the slope is going to be, no, you're on the right track, it's an average, but it's rise over run. So if I look at the m secant, change in y now, the y-axis is no longer y, we're tracking x, position, right? So the change in the dependent variable is going to be displacement, right, delta x. The change in the independent variable, the x variable, in this case is t, it's going to be change in time. So what's that look like? Average velocity. Sure. Okay. So this is telling me that after 2 seconds, I'm at this position. After 4 seconds, I'm at this position. Well, on average, I changed my position at a rate of, who knows, this value, whatever the slope is, that's my average speed. Was I going that speed the whole time? No, I wasn't. I started off going slower, and I ended up going faster. But that was the average speed, right? That's easy to calculate. What Newton and Leibniz sought to do with calculus was something a little trickier. What they wanted to do is they wanted to find not the average. I want to know, for example, I'm about out of time, aren't I? Yeah. Okay, this would be a great setup for tomorrow. So what they wanted to know was at this spot right here, what's my instantaneous rate of change? What's the slope of the tangent line? Okay. in terms of kinematic quantities, that would have been my instantaneous velocity. Okay, yeah, it was tricky. It's very tricky to do, but we get a real elegant, simple solution with calculus that I'll tell you tomorrow.
Yeah, thanks for giving us the physics lesson.
That's right.
During it.